Hi, physics students, and welcome to this lesson about horizontal projectiles. Please have your notes ready from class, and we're going to go over some of the key concepts about horizontal projectiles and problem solving.
Well, to start our conversation, you might be asking yourself, what is a projectile? And I want to go over a couple key ideas to help us identify when motion is projectile motion. So there's a couple very specific details to pay attention to. Number one, gravity is the only force acting on the object. So for example, if you're throwing a ball and that ball is moving as a projectile through the air, it we are going to consider it a projectile only if gravity is the only force acting on it. Therefore, we're not going to start talking about it as a projectile as it gets accelerated, but at the instant it leaves a person's hand. And that's really important because that instant it leaves a person's hand, gravity is the only force. We're going to always ignore air resistance. And then, more importantly, we can consider x and y separately. So for the x or horizontal, we'll always use our equation without acceleration. Velocity is distance over time. And for the y, we can always use our four other motion equations that include acceleration. That happens because if we consider gravity being the only force, which direction does gravity act? Hopefully, you said up and down. Therefore, that's the y direction, and that's where the acceleration is going to take place. As a really quick review, remember when we're dealing with constant velocity, we can use our velocity is displacement over time equation. However, if there is an acceleration or a changing velocity, we need to use one of the other four motion equations. How we're going to decide which one to use, we'll take a look at that more in detail with some future problems.
I know I've reviewed this before, but if these are our four motion equations, we can look at what's given in the problem. And notice this first equation is missing the distance. Now these are units. This is meters, seconds, meters per second, and meters per second squared. So if meters is missing, that means the distance is missing. Therefore, I won't be able to solve for distance or use it as one of my values initially if I use that equation. Similarly, I'm going to look for the things that are missing, and I can then solve for the different quantities using the different equations. Now, you just have to kind of look and see what the problem gives you and kind of work from there. These do work in the y direction when we're talking about projectiles. They do not work in the x. So I want to make sure you have that clear in your mind as we go forward.
Really understanding the physics and the ideas behind projectile motion helps us solve problems like this one, where it seems like we don't have enough information. In this case, there's a ball that is going to be dropped and it's going to hit the ground. We want to know how long it takes, but we only know the distance that it falls. We need to go back to our physics, which are those key ideas that we just talked about, where if we have a free fall motion problem, projectile motion, gravity is the only force acting on it. Therefore, even if they don't give us a value, we know that there's a uniform acceleration which is equal to negative 9.8 meters per second every second. So we can put that in for acceleration. I call these hidden values because the problem doesn't explicitly tell us, but it's really important to help us solve and understand how to find the actual answer given the information that they're giving us. So that's where the physics comes in. I always want you to be thinking about that when you're going through these problems. It's more than just a math problem. It's using our concepts about the physics to help us understand the problem more in depth. Okay, so the other hidden value we know is that it starts from rest. So the initial velocity is 0. Now we can go back to our equations and solve for time. I know 3 of the things, and so I can find an equation that has initial velocity, displacement, and acceleration, and I can solve for time. I think the best one to use is the displacement in the y direction, because we're accelerating in y, is equal to that initial velocity times time plus 1 half gt squared. I already know that the displacement is 25 meters, and it's going to be negative because it's going downwards from our start. And I also know that the hidden value of initial velocity is 0, so that term actually goes away. Rearranging and substituting in, I get 1 half equals 1 half gt squared equals the dy. Now I can solve for time. So I'm going to multiply both sides by 2. So I have 2 times dy. And then I'm going to divide both sides by g because it's g times t squared. Finally take the square root of both sides. My new equation, I can substitute my numbers in, or I'm taking 2 times the negative 25 and the square root of that divided by negative 9.8. Luckily, a negative and a negative divided will create a positive, so we don't have to deal with that with our square root. And we end up with the time value of how long it takes for the ball to fall that 25 meters when we only knew the initial distance dropped. Now that's pretty cool. We can use our equations to not just find the hidden values, but use our knowledge of science and physics to find that time, which is 2.26 seconds. In our last example, we just took a look at an object that was falling straight down. But what if, at the same time it's falling down, it also has a horizontal velocity and a horizontal component? So as you see here, this 10 meters per second is the ball is going to the side and falling at the same time. My question is a classic one. Which ball will have more airtime? Or in other words, which ball will hit first? Pause the video, consider this for a second, and then start it again after you make your assumption and your guess. The classic Mythbusters actually did this exact experiment and fired a bullet and dropped a bullet from the exact same height at the exact same time, and notice what happened. I'll try to link a video so you can watch this on your own, but we'll talk through some of the science in the next slides. Believe it or not, the balls actually hit the ground at the exact same time. So one doesn't have more air time than the other. The time it takes to fall and the time it takes to move to the side and fall is exactly the same. So let me explain this. When we look at motion, and if I take a stop motion at the same interval of time of a ball falling down, I notice it's definitely accelerating. But if I do the same thing of a ball that's moving through the air horizontally and vertically, at those same instances of time, it's fallen the exact same amount. That's one way of kind of talking about the idea that the air time or the fall time will be exactly the same. So here we go. I'm lining them up. At every instance, they have fallen the same amount. So the one that's launched is just like a free fall problem in the vertical motion. They match up exactly the amount of distance that it covers in the amount of time from drop straight down or launch to the side. And this is because the vertical components, the accelerated motion in y, is independent of any velocity that might have in x. Those two are completely independent from x and y, independent from each other. Before we talk about a problem that has both x and y, let's consider some of the things we know. Our physics tells us that the x velocities never change. So the initial velocity and the final velocity in x stays the same because there's no acceleration. And in the y, the acceleration is negative 9.8 meters per second every second. So the y will change values between our initial and our final over a certain distance. The other thing to keep in mind is that the time it takes to fall in y is the same it takes to travel in x. So the time component will be the same for both of those. We can use that to our advantage, thinking of these problems as just free fall problems to start with, and then we can bring our other equations into play. So if we want to solve for something in x, we can then use our d is equal to velocity times time equation because we know that x velocity is the constant throughout, and there is no acceleration. So I'm going to show you an example with that on the next slide. So this problem should look really similar, except the ball has an initial velocity horizontally. How do you solve these? Well, think back to the physics. What do we know? Think of this as a free fall problem at first. So we're going to solve for things vertically only. Start with the vertical. And this should look really familiar. We're going to solve for the time. How long does it take to fall those 25 meters? We'll plug in our kinematic equation, and knowing that the initial velocity is 0, our distance is 25, and our acceleration is negative 9.8. We should get the same answer we got before because we're only talking about the vertical. Our next slide is we'll combine that horizontal, but this is key. We need to know this time. It's a bridge between the horizontal and the vertical. All right, great. Now we can tackle the idea that there is a velocity in the x direction of 10 meters per second. It's the same as the initial and the final because there's no acceleration, and the time it takes for that to happen is 2.26 seconds because that's the same in both x and y. Solving now for what we know that the initial velocity in y is 0. It's going to fall 25 meters, and it has an acceleration of negative 9.8. We want to solve for how far it travels horizontally. Now, remember that the time is equal. So we already know the time it takes in y is the same as the time it takes in x. And the velocity is constant. Therefore, there is no acceleration. We can use our distance is equal to velocity times time equation. So we're going to plug that in. We want to solve for the distance in x. We know the velocity in x is 10 because it doesn't change. There's no acceleration. And we know the time is 2.26 seconds. Therefore, the distance it travels horizontally is 22.6 meters. All right, hopefully that makes sense. We're going to take a look at a different example. Again, there's not enough information, it seems, at first, but we're going to use our physics to figure out what's missing. I'm going to map this out without numbers first to show you kind of the physics thinking behind it. We want to find out what VI is, and VI is pointing completely horizontal. So we want to solve for the initial velocity in the x direction. In order to do that, we need to know how far it travels in x and how long. Velocity is always distance over time for x values because there is no acceleration. Key point, physics number 1. All right, number 2 is what we're going to do is we're going to try to find the final resultant velocity. Now that is going to be a combination of both that x velocity, and we know it's a projectile that's being pulled by gravity at the same time. It's falling, and it's going to have a certain y velocity as well. We need to find that out, and then the resultant is the combination. Think of a right triangle, think of vectors. We'll be able to put the x horizontal and the y vertical together, making a right triangle, and the resultant or the hypotenuse will be the velocity we want to find. That will be the impact speed that this dart or whatever it is going to hit the wall. The angle will be then measured from the horizontal down, and it's that interior angle. All right, so these are some big physics ideas that we're going to do. I'm going to do an example problem with numbers next, but I want to make sure you remember concept-wise, the x velocities never accelerate, so the initial and the final will be the same. Often the initial y velocity is 0, and we'll have some kind of final y velocity. The problem may or may not give it to us. It doesn't give it to us in this example. And we can then plug in our other hidden values, right? We're solving for dx. We might know a dy. They might tell us how far it falls down, or they might tell us even how far over it goes. So we could use dx and dy. And we always know the acceleration in y is negative 9.8 meters per second squared. The time, other key concept here, will be the same for both the x and the y components. Now, it might ask some questions about the straw speed, the impact speed, and the impact angle. Now, remember that triangle. That's going to help you kind of break this down into those different speeds. The straw speed is the Vx. That's how fast it might be flying out of the straw. The impact speed is your resultant of the x and the y combined together, and the angle is the angle measured in that interior to give that final velocity a direction as well, that theta. So think of that triangle. You're going to build a new triangle given the velocities that you calculate in both x and y. All right, time to put things together. We're going to take a look at a spit wad flying out of the straw, traveling a distance of 1 meter from the end of the straw to the wall, and then a vertical distance of 15 centimeters or 0.15 meters. We're going to try to find our initial velocity, x, so the straw speed, the speed that it was traveling as it left the barrel of the straw, and also our resultant velocity and angle. Now, to do that, we have to apply some of the physics that we just talked about. In order to find our either the velocity in x, we're going to need to go back to some hidden values that we have, and also remember our physics about the time. I'm always going to want to solve for time because it's the bridge between the x and the y first. So I know my initial velocity in y is 0. I can use the dy. I know it traveled 0.15 meters in the and it's accelerated at negative 9.8 meters per second squared. So I can solve for time. I'm substituting the numbers in. Dy is 0.15. I'm rearranging for t. I'm going to multiply that by 2, divide by 9.8, and take the square root of it to find out how long it takes for that spit wad to fall this distance. Now that could be just off the end of the barrel, or because it's the same time if it is shot horizontally, if it falls this distance over here as well. Okay, so that's 0.17 seconds. Remember that. We're going to put that into our table. Remember to use that when we're calculating our velocity in x. I can use that because the time it takes for us to travel from here to here is the same time it takes for us to fall this distance. Okay, so then I can use that time and divide 1 meter by the time, 0.17, and I know the initial velocity, or the straw speed, is 5.88 meters per second. That's also the final velocity in the horizontal direction because there is no acceleration horizontally. Okay, so that's important because in order to find the impact speed, we need to combine the horizontal velocity of 5.88 meters per second with the vertical velocity. Now, I don't have that vertical velocity yet, but I can use some of my physics equations to find it. And when I do so, I'm going to build a small right triangle with vectors. Here's my right triangle, and I'm going to use this black vector as the impact speed. Hopefully this is making sense, kind of thinking back to some things we've learned previously. Now, in order to find that y velocity, that final velocity in y, I can go back to my acceleration equations, right? Because their motion is accelerated at negative 9.8 meters per second squared. So I can take the initial velocity plus acceleration times time. You know it. The time you're going to use is the same time you calculated in the first part of the problem because it's the same for both x and y. The initial velocity is 0, so that cancels out. Taking the 9.8 times 0.17 will give me my final velocity. I'm going to put a negative in there because that indicates the direction. It's pointed downwards, so negative 1.67 meters per second. All right, now I can go back and use my SOHCAHTOA to figure out the angle, and I can use my Pythagorean theorem, a squared plus b squared equals c squared, to find that missing side. So those are the two last pieces. When it talks about impact speed and impact angle, we're really going back to the triangle, right triangle built of the velocity in x and the velocity in y. So let's find out what that hypotenuse is. We're going to take the a squared plus b squared equals c squared, using the 5.88 meters per second squared as my a side and the 1.67 as my b side. And then I can take the square root of both those. And that will tell me what the impact speed is. That will tell me what this resultant is after combining these two vectors together. All right, so the terminology is really key. Make sure you're looking at what velocity the problem is asking you to solve for, and then going from there. All right, so that becomes 6.12 meters per second. And the last thing I need to do is use my triangle one more time and SOHCAHTOA to figure out the missing angle. All right, so I'm looking for that theta right there in the corner of the triangle. It's measured down from the horizontal, and I can use SOHCAHTOA. I could use a hypotenuse, but I'm probably going to stick with the values that I calculated first to avoid a lot of rounding misconstrueds. So I'm going to use tangent. So the tangent inverse will solve for the angle, and tangent is always opposite over adjacent. Now, the opposite side in this case is our Vy, and the adjacent side is our Vx. So I'm going to plug those things in, and I get about 15.86 degrees for my impact angle. Please reach out as you're thinking this through. It's a combination of both math and also our big key physics ideas. So go back to the first slides if you need a refresher on those. Reach out if you have any questions. Thanks, and have a great time doing physics.